Thank you all for coming today. I'm really excited to speak to you about quantum paradoxes. So quantum mechanics is a really counterintuitive, but also really fundamental theory. And in this talk, we're going to be going all the way from the really core fundamental concepts to the cutting edge of the technology that people are building today. And I'm going to be also introducing some recent research that I've been looking at to give you an insight into some of the ideas that I think are really have changed my perception of quantum mechanics recently. So quantum mechanics, you've all probably heard of it before. It's our best theory of how matter behaves in the universe. And it's really, really precise. It tells you with kind of the highest degree of accuracy that we've ever been able to figure out how matter behaves. But also people debate a lot what it actually tells us about reality. And these debates are really quite dramatic. So one of the main controversies around quantum mechanics is whether or not it tells us that we live in a multiverse. And I'll explain during the talk why some people think that it is saying that we live in a multiverse. And overall, what we're going to look at today is 5 different ways of testing this idea. Because often when we talk about whether quantum mechanics is telling us that there's a multiverse or not, people think it's just a philosophical aspect of quantum mechanics. It's not really the scientific part. But what I want to show you today is that it's actually part of the really core aspects of the science in quantum mechanics. So let's start with our first way of testing the multiverse. We're going to start with Schrödinger's cat and a particular twist on this famous thought experiment. So to start with, I'll just explain the Schrödinger's cat thought experiment. So Erwin Schrödinger, back in 1935, imagined that there was a cat trapped in a box. But it's trapped with a radioactive atom and a vial of poison. And what happens is this atom has some probability that it might decay, or it might not decay. If it decays, then it will trigger the hammer to smash open the vial of poison, and it will kill the cat inside the box. If the atom does not decay, then the hammer does not trigger the poison, and the cat stays alive. Now, the twist with quantum mechanics is that a radioactive atom could be in a superposition of having decayed and not decayed at the same time. So there's a certain quantum state where it's both decayed and not decayed in part of that state. So then you can ask, well, what does quantum mechanics say is going to happen inside this box? So if you describe each part of this thought experiment using quantum mechanics, then what we get is a chain reaction. So the atom is in this superposition of having decayed and not decayed, and then it interacts with the hammer. Once it interacts with the hammer's in a superposition of having smashed open the poison and not smashed it open. And so the poison then joins the superposition. And then once the poison interacts with the cat joins in the superposition. So according to quantum mechanics, if we apply it to everything inside this box, we end up with the cat also in a superposition of being alive and dead. There's the alive part of the state where the atom has not decayed, and then the dead part where the atom has decayed. And then we're presented with a situation where when we open the box, the cat we're just going to see it either alive or dead. And this is known as the collapse that happens when you measure a system in a superposition. So now we come to the core controversy around quantum mechanics, which is, does this collapse actually happen or not. So there's two approaches to explaining this, what's happening in this thought experiment. There's the single world approach, and there's the many worlds approach. The single world approach says that when you make an observation of a quantum system, something is actually going to irreversibly collapse into a single state. So when I open the box and look at the cat, it's going to collapse into being either alive or dead. You might say that the cat is actually an observer itself, and so the cat, when it measures the radioactive atom, it already collapses it to a single state. So in this single world approach, the cat might never actually be in a superposition in the first place because it causes this collapse. The alternative is the many worlds explanation. So what this interpretation says is that, well, we're all made of atoms, right? These are systems that are described by quantum mechanics. So us, as observers, we're also described by quantum mechanics. So we should carry on applying this reasoning that we had inside the box to us as observers outside as well. And if we do that, then it means that once we open the box and look at the cat, we become entangled with the cat, and we enter this big superposition state as well. So there's one version of you that saw the cat alive, and another version of you that saw the cat dead. And these branches both physically exist in the many worlds interpretation. So the idea is that this superposition keeps expanding until everything branches off into these two different branches of the world in superposition. So that's the idea of these two different interpretations. And you can imagine the single world version as reality just moving along a single branch, whereas in the many worlds case, we've got reality branching off like all the branches in a tree. Okay, so this is the part where people will usually say these are just philosophically different interpretations. But there was a thought experiment that was proposed in 1985 that demonstrated that these are actually scientifically different interpretations. And now I'll explain the setup for that. So the idea is that in the single world version, when you do a measurement, when the cat does a measurement of the atom, it collapses irreversibly into either decayed or not decayed. Whereas in the many worlds version, everything is reversible. Because you've become entangled, you've entered these multiple branches, in principle, you could reverse that measurement, and then the atom would go back to the state that it started in. So the idea of this thought experiment, I like to imagine that we have an Uno reverse card. Who's played the game Uno? Yeah, quite a lot. Yeah, so it's a card game where you can play different cards round in a circle, and you can play an Uno reverse card to reverse the direction that you're playing. And I like to imagine that in the Schrödinger's cat thought experiment, everything's moving along, but then you play the Uno reverse card and try and reverse the measurement. So why would this give a test of the many worlds? Well, if the single world interpretation is correct, then if you try and reverse Schrödinger's cat, the atom will end up randomly being either decayed or not decayed, because it's irreversibly collapsed, so it ends up kind of randomized. Whereas, if we're in the many worlds case, where both the branches really exist, then we can do this reversal properly, and the atom ends up back in the state that it started. So if you do this experiment lots of times where you try and reverse the measurement, and then you check what state the atom has ended up in, the single world case, you'll get just random outcomes, and in the many worlds case, you'll get back to the initial state every time. So that's the idea for how you could imagine testing between many worlds and a single world. But it might sound a bit far-fetched to actually control all the atoms inside a cat in order to reverse this measurement. It's a very intense, dramatic experiment to do. You can kind of imagine it in a thought experiment, but it is hard to see how you'd actually do it in a lab. But the person that proposed this thought experiment, David Deutsch, in 1985, thought of a different way that you could imagine running this kind of experiment. And that is to run it on a quantum computer. So this is where the idea of quantum computing first came from, which I'll talk a bit about now. But the idea is that because it's so difficult to actually control the atoms on the cat, you imagine instead having a computer that's running a simulation of it. And then you apply the reverse process on the computer instead of on the physical system, and that lets you do this experiment to test the many worlds versus single world. But to do this, you'd have to have actual quantum hardware. The hardware of the computer would have to be able to be in superposition in order to do this experiment. And this led to the idea of a quantum computer, which is a computer built from hardware which can be in superpositions of states. So now I'll introduce the kind of basics of the quantum computing, because it'll come up in our later ways of testing the multiverse as well, with some more recent developments. So how do we actually build something to build this kind of computer that can run a simulation of a measurement? Well, classical computers are based on bits. So you can imagine bits being like the two sides of a coin, where we can have heads or tails. That's one bit of information. You could flip from 0 to 1 and 1 to 0. And all of our normal computers are encoded for in a series of bits, a series of ones and zeros. With quantum computers, instead you build quantum bits. So quantum bits you can imagine on the surface of a sphere, which I like to compare to a Lindt chocolate truffle. So on a quantum bit, the top of the sphere is 0, the bottom of the sphere is 1, but you can also be at any other point on the surface of the sphere. And each of these points are a superposition of 0 and 1. So they're all a different quantum superposition. And then when you do a measurement of this qubit, you'll find it collapses to just one outcome. So you either collapse it to 0 or you collapse it to 1 with some probability. So if it's closer to 1, you'll get 0 more likely. If it's close to 1, you'll get 1 more likely. 0, you'll get 0 more likely. And that's how you control your computer. You manipulate these qubits and then do measurements on them. So the measurements on the classical bits are the operations you do are flipping the classical bits. With qubits, instead, you rotate around this sphere to manipulate them. So once you do that, you can then do computations, and you can build a device. Now, in my day job now, I work at a quantum computing company, so we're trying to build computers out of these things and actually build qubits. And there's lots of ways to actually build them. You can build them out of atoms, out of photons, particles of light, or out of superconductors, which is one of the most popular approaches that the big tech companies like Google and IBM are doing, and so is the company that I work for, which is a startup called OQC. And this is an example of what the chip of a quantum computer can look like. So this has these superconducting islands. Each of those dots is a qubit. And then that chip ends up inside the silver canisters that you can see in this picture. So what's actually in the picture, this thing that looks like a chandelier, is a fridge which cools down chips close right down to absolute zero, so they can behave quantum mechanically in a way that we can control. And this is a scientist working on that, and then you'll find the chips in those silver parts at the bottom. So that's what a quantum computer looks like. They actually exist and are running today. And we will come back to quantum computers later on. But for now, just to recap this first way of testing the multiverse, we can imagine running a simulation of an observer doing a measurement, like Schrödinger's cat does, on a quantum computer, and then try and reverse it and see if we can reverse successfully or not. So that's the first test, but it's pretty far-fetched. In order to do that, we'd have to have a fully working quantum computer, which we don't yet, and we won't for some time. And we would also need to figure out how to simulate an observer, how you simulate someone thinking on a computer, which we're not really close to doing yet. So it's pretty far in the future. But what if there's some experiments that we could do right now, or more closer, in order to test the multiverse? So that brings me to the next proposal, which is called the quantum bomb tester. This is a thought experiment that was thought of in 1993 by two physicists, Avshalom Elitzer and Lev Weidman. And it's a way of doing something with quantum mechanics that's pretty dramatic that you can't do with classical physics. So for this thought experiment, imagine that you have a box, but you can't see what's inside the box. You're told that it's either empty or it contains a bomb, which I'm going to represent by this Terry's chocolate orange. So this bomb is a highly sensitive bomb, which means that even if a single particle interacts with it, then it will explode. So you can imagine with photons, particles of light, if even a single particle of light interacts with it, it's going to explode. And so the question is, can you figure out whether or not there is a bomb inside this box without the bomb exploding? Now, if you try and imagine doing this normally with classical physics, you can imagine, okay, maybe I can not touch the bomb. I'm just going to send in one particle of light to take a look if it's there or not. But you can't do that, because if the bomb is there, then that single particle of light is going to explode and destroy your bomb. And it's game over. But remarkably, with quantum mechanics, there is a way of figuring out whether the bomb is in the box without it exploding. And that's using something called an interferometer. So the idea of the interferometer, I'll walk you through this setup we have here. We have a source of photons. So what this source does, it throws out single particles of light. And then it comes up against something called a beam splitter. What this is a half-silvered mirror, which is able to create superpositions. So when a photon hits the beam splitter, it splits into a superposition of going straight through it and reflecting. So it splits into a superposition of two paths. Then we have mirrors, which just reflect these parts of the photon so that they end up back together, and they meet at a second beam splitter. Now, here's where the kind of interesting quantum aspect happens, because we get interference. So you can get interference, let's say, in normal life with waves. If you have water waves, you can get constructive interference, where the waves combine together to make a larger one, or you can get destructive interference, where the waves cancel out and then you've got nothing. The same can happen here, but on a quantum level with a single photon. So when the two parts of the superposition of the photon meet at the second beam splitter, they have this constructive interference, which makes them merge back into a single photon that will come out again. So I'll show you an animation of this process working when there's no bombs or anything. We're just looking at the interferometer by itself. So we send the photon through. It splits at the first beam splitter. We reflect the two parts together, and then they merge, and we get a click at a detector, which tells us where the photon was detected. All right, how does this help us figure out if there's a bomb in this box? What we do is we introduce the bomb in one path of the interferometer. So imagine that the bomb is in this bottom path. So now what's going to happen is that when we have this superposition of the photon, it's going to come up and interact with the bomb. So the bomb essentially is going to measure whether the photon is in the bottom path or the top path. And we saw before that a measurement causes a quantum collapse. So once the bomb measures the pathway of the photon, it's going to collapse into either the bottom path or the top path. So if it collapses into the bottom path, then we have a problem. The bomb is going to explode, and it's game over. So let's see this happening. So we reached the bomb. It collapses into the bomb pathway. The bomb explodes. But what happens if it goes in the other path? Well, then it collapses into the top path, and it just keeps going. And it reaches the second beam splitter. But now there's nothing to interfere with, because the other part of the photon isn't coming back to interfere with it. It's just by itself. So now it's going to split equally between the two detectors. And then once the detectors measure the photon, it's going to collapse onto one of those two. So one possibility is that we end up with the same detector as before going off, the same detector as when there's no bomb there at all. So that's the horizontal one where they merged and made that one click. So if that happens, it doesn't tell us anything about whether or not there was a bomb, because it could have happened whether there was a bomb or if there wasn't one. Now, the other option, this is the interesting one, is that the other detector is the one that clicks. So in this case, we collapse into the top path, we reach the second beam splitter, and now the top detector clicks. Now, that could only have happened if the bomb is there. So if you imagine that you did this experiment with the bomb possibly being in the box, then you get this outcome where it clicks at the top detector, then you know for sure that the bomb was definitely there, because if the bomb wasn't there, you couldn't have got a click at that detector. So somehow you've managed to figure out that the bomb was in this path, even though absolutely nothing has interacted with it. Even a single photon interacting with it would have made it explode. Now, this is, I think, one of the most kind of counterintuitive aspects of quantum mechanics. And one of the authors of the paper, Weidmann, suggested that this is really a paradox that needs explaining. How could you possibly figure out that there was a bomb in this region of space when there's only been a photon physically in another region of space? And he suggested that we need an explanation for this. And his answer was that it must have exploded in another branch of the multiverse. So according to the multiverse interpretation of quantum mechanics, both these paths of the photon really happened in the superposition. And then once one of them interacted with the bomb, then we actually get both the possibilities I showed you happening. So we end up in a superposition where in one branch, the bomb explodes and the photon collapsed in the path with the bomb. In the other branch, the photon collapsed in the other path and the bomb didn't explode. So if both those possibilities really happened and we're in a superposition of both of them happening, then that means that the bomb did interact with the photon somewhere in the multiverse. So it can explain why we were able to find out where the bomb was, even though it looks like we didn't interact with it in this branch of the multiverse that we've ended up in. So it's a controversial line of reasoning. It was made in this paper in 1993. It's not convinced everyone that the multiverse is real, but this experiment has been done with items that are less dramatic than bombs, like modeling them as atoms instead. And it does actually work. So if you're convinced by this argument, then we've already tested the multiverse. But that might not be enough. And so far, we've only really been talking about superposition and this phenomenon of superposition between branches and the multiverse in that context. But there's an interesting alternative way to consider the multiverse versus single world theories through a different important phenomenon in quantum mechanics. And that one is entanglement. So quantum entanglement is kind of one of the major aspects of quantum mechanics, which is still causing a lot of controversy today on debating the way that it works. And it's really core for a protocol called quantum teleportation. So what I'm going to do now is explain how quantum teleportation works, and then why it's a way of testing the multiverse as well. So, entanglement. If you have a pair of socks and you move them really far apart, and you don't know whether the pair of socks is, say, blue or pink, and then you open a box with one of the socks in it and you look at it and you see that it's pink, then you know for sure that the other sock must also be pink. So this is classical correlation between two systems. Now, in quantum mechanics, we can have a phenomenon called entanglement, where we get correlations that are stronger than are possible classically. So you can imagine that you take two qubits, you let them interact in such a way that they become entangled, then you move them far apart, and then if you measure one of the qubits and you get a particular state, then you know for sure that if you measure the other qubit, you'll also get that state. Now, that much is just the same as classical correlations, but it turns out there's another way you can measure the qubit, and even if you measure it that way, you still end up with the same outcome on the distant entangled qubit. And because of this, it means that the correlations that you get between the entangled qubits are stronger than is possible with any classical system like SOX. So we've got this kind of super correlation between these systems. And this was famously described by Albert Einstein as a spooky action at a distance, because it's often thought of as the idea that if you do something to one of the qubits or measure one of the qubits, you're instantly influencing the one that's a distant place away from this one. So entanglement has really confused a lot of people and surprised a lot of people. So how is it useful for quantum teleportation? For this thought experiment, imagine two characters. We have Alice and Bob. And Alice wants to send a qubit of information over to Bob. So let's say this is the qubit that Alice wants to send, and it's just some information is some unknown state. She doesn't know what state it's in, but she wants to get it over to Bob. So what we do is we create a pair of entangled qubits, and we give one of them to Bob and one of them to Alice. And then Alice does a measurement on her special qubit that she wants to transport over and her entangled qubit. And when she does this measurement, she's going to get two classical bits out. So it's either going to be 00, 01, 10, or 11. They're the four possibilities. And she sends them over to Bob. So we can represent the classical bits as some coins. She can encode her outcomes that she got, and then she can call Bob up on the phone and tell him what these numbers are, or she can text him or communicate with him classically however she wants and send over this classical information. Then, based on what these two numbers are, Bob applies an operation to his qubit. And somehow, once he's applied that operation, it ends up in exactly the state that Alice wanted to transport. So why is this called quantum teleportation? What's teleporting here? The idea is that Alice had this quantum state, this qubit over here. And then somehow she only physically sent over two classical bits of information. But by this protocol, Bob was able to end up with Alice's qubit of information. So the weird aspect of it is that somehow we've managed to transfer a qubit of information over from Alice to Bob just by physically moving two classical bits. And that seems like a paradox of how is it possible to move a qubit just with these classical bits. And people will usually say that Alice and Bob have this shared entanglement that they shared beforehand, and somehow the qubit of information ends up kind of jumping across that entanglement in some kind of spooky way using this spooky action. So this is just a diagram of the idea. We've got these entangled qubits shared by Alice and Bob. Alice does her measurement, sends over the classical bits, Bob receives them, and gets his version of Alice's qubit. But it presents us with this problem of how did the quantum information jump over? And the many worlds interpretation of quantum mechanics offers an interesting solution. So this solution is that the classical bits are actually secretly quantum. So they're disguised quantum bits that appear classical. So in the many worlds interpretation, the measurement device that Alice uses to actually measure her qubits, that's actually going to be a quantum system as well. It's made of atoms, like us. It's described by quantum mechanics. And so in the many worlds interpretation, you'll describe that measurement device as a quantum system, and we can keep this quantum description of everything moving throughout the experiment. So when we apply this many worlds view to measuring qubits that are entangled, it gives us a different interpretation of entanglement to the usual one that you'll read in accounts of entanglement. So, as I mentioned, usually we'll have this idea of information jumping through entanglement. But in the many worlds view, instead, you get the view that if you have two entangled qubits, then they actually act as lock and key pairs. So you can imagine information locked up in one of them that can only be unlocked if it interacts with the other one. So I like to imagine this using Kinder eggs. Who here is familiar with the Kinder Egg or has ever had a Kinder Egg? Okay, quite, I think most people. So the Kinder Surprise is called a Kinder Surprise because there is a surprise inside. So these eggs have just a chocolate on the outside, but if you open them up, then you'll get a surprise, which is a thing which has a little toy inside that you can build. And you can imagine the entangled qubits that form these lock and key pairs are like Kinder eggs that contain information or can contain information locked up. And then you only access it once they interact with their entangled pair, and then that unlocks it, and then you get the information that was trapped inside. So that's what view of entanglement, this kind of many worlds approach, leads to. How does that help us with explaining quantum teleportation? So let's walk through the quantum teleportation experiment using this locked up qubits view. So now what's happening is that when Alice does her measurement on the qubit that she's teleporting, she's actually getting that information of the qubit that she's teleporting locked up inside the qubits. So they become like the Kinder eggs, but with the information locked up inside. And then what you think are classical bits are actually qubits. When you measure them, you'll just see 0, 0, 1, 0, 1, 1, and so on. But there's actually information hidden inside which is storing that information of what Alice's qubit is. And so if you then move the classical bits over to Bob, you're actually moving these qubits that have locked up quantum information. And then Bob unlocks that information with his qubit and then is able to get Alice's qubit out. So we have this kind of fully local view of teleportation. So it looked at first like something's jumping across, but really, in this view, we can see the information actually just locally being transferred by being hidden in these qubits. So we end up with another difference between the single worlds and the many worlds. In the single world version, where the measurement just collapses the qubits, then we don't have an explanation for how the information gets transferred, the quantum information, over to Bob. We end up having to say that it jumps somehow. So you have to accept that there's some kind of instant communication possible, instant influence possible between entangled qubits. But in the many worlds picture, we can actually track how the information is moving, but we have to accept that there's this inaccessible information that's stored in what we think of as classical bits. So this experiment, quantum teleportation, has actually been performed. People have done this now. The experiments doing this were part of what got the Nobel Prize in 2022, and it all checks out. So if you're convinced by this argument, then those experiments are a way of testing that many worlds works in this for this experiment. If you want everything to be local, you can also sacrifice the locality and have things jumping around if you prefer the single world theory. So technology has reached this point where we can do experiments like quantum teleportation. And quantum teleportation is one of the components that comes into quantum computing more generally. So with quantum computing, we'll have a bunch of these qubits, and we'll apply these operations to let them all interact. And it turns out that there are some algorithms which let you perform some computations on a quantum computer much, much faster than would be possible on a classical computer made of bits. And there are lots of different possible applications for these quantum computers. One of the most famous ones is that they could break cryptography, break encryption. So there is an algorithm called Shor's algorithm, which was proposed and shows that using a very good quantum computer, you would be able to break the encryption that's core to a lot of our cybersecurity today, like our bank details and internet access and so on, called RSA. And this, amongst many other applications, has led to a kind of global race between big tech companies and startups and academic labs and lots of different places to build a quantum computer that works and can run some of these revolutionary algorithms. So this is a very kind of fast-changing space, and lots of new announcements are happening all the time. It's hard to keep up. Could you raise your hand if you've heard of the Google Willow chip? Has anyone heard of this? Okay, quite a few, I think maybe half or so. So in 2024, Google made a big announcement about a quantum chip that they had built. So this is a chip with a lot of these qubits, and they used it to run a certain computation. And for a while, we've had the idea of achieving a point where a quantum computer can run something faster than a classical computer would be able to. We've not really reached the point where that's been done for a useful problem yet, but it's been done for some problem. And Google made an announcement along these lines of saying that they demonstrated a problem that would take 10 septillion years to do on a classical computer. They managed to run it on their quantum computer. But what's particularly interesting, or was particularly interesting for me about this announcement, is that, so this is an excerpt from a blog that someone on the Google team wrote about this announcement. And they mentioned the multiverse. They said that the fact that this takes 10 septillion years would take 10 septillion years on a classical computer, and they managed to do it on a quantum computer, is showing that it at least lends credence to the idea that quantum computation occurs in parallel universes. So what I'd like to do now is just summarize the kind of reasoning of why you might say that it's demonstrating the multiverse, and then what I think about what it's actually demonstrating. So let's walk through what the reasoning is here. So we know that quantum computers could perform some computations much faster than classical computers. And that's what Google have demonstrated amongst other people. And they make the point that even if you took all the atoms in the universe and built a classical computer out of them, there wouldn't be enough matter to build a classical computer that could run this algorithm in a reasonable time. We just wouldn't be able to. So it kind of really goes beyond the physical limits of what we have access to. And then this poses us with a question of, well, where did that extra computation happen? If all of the atoms in the universe wouldn't be enough to do the computation, where did it happen? And some scientists suggest that it must be accessing these branches of the multiverse in order to do the computation. And so the argument goes that because we've done something that's used all the atoms, that's gone beyond if you used all the atoms in the universe, is showing that we really must be accessing these other aspects of reality that happen when systems go into superpositions. And that's been used to explain how quantum computers do anything faster than a classical computer could. Now, I think there's something to this argument, but if we go back to our interferometer that we used for the bomb tester, you could say the same thing about that scenario. So if you have a photon that goes into superposition and then has interfered with itself to merge back into a single photon, then we know that those two branches, the two parts of the superposition, must have both been kind of physically real to some extent because they merged together back into one. We saw this constructive interference happening. And you might have heard of the double slit experiment. This is another famous fundamental thought experiment and actual experiment done in quantum mechanics, which shows a similar thing to the interferometer. The idea is that you send a single photon through two slits, and you see a pattern of it interfering with itself, so of having this constructive and destructive interference. And so even this kind of experiment can only be explained if these different parts of the photon are really both going through those slits. So my take on whether the quantum computing announcement demonstrates the multiverse is that it kind of does, to the extent that you would also say that the double slit or an interferometer does. But it's more like an extreme, exaggerated version of those than something really distinct. But it's an interesting idea to consider the fact that it's really pushed it so far to the extreme that it's beyond even all the atoms of the universe. But I see it as like pushing the boundaries of this experiment further, but we already saw it even with two slits. So if you're convinced by two slits, you might be even more convinced by the chip. So now our final way of testing the multiverse is an idea that I've been working on recently to do with communicating across the multiverse. So often when you introduce the many worlds interpretation to people, a natural question is to ask, well, can I speak with the person in the other branch? Can I communicate across the multiverse? And my usual answer is no. And so someone asked me this question. We were chatting a few years ago, and I said no, because once the branches are separate, they're separate. You can't go and access a different branch or communicate with yourself in a different branch. And I'd heard this said multiple times, but I wanted to check by myself, why actually is that the case? Is there some kind of fundamental principle that's stopping this information transfer happening between the branches? Like, what is it exactly that's stopping that? And when I was having a look at it, I actually thought there might be a way around this using a trick. And this trick is similar to the trick we saw at the very beginning in the first way of testing the multiverse with imagining reversing Schrödinger's cat, but in a different kind of scenario. So what I imagine for this is something called a Wigner's friend thought experiment. So in general, these types of thought experiments are ones where you imagine that you've essentially got this observer simulated on a quantum computer. We're kind of in that setting. And then there's someone on the outside called Wigner who is controlling the friend who's simulated in the quantum computer. And so Wigner and the friend can agree beforehand on the experiment they're going to run, and then they run this experiment. So let's walk through how multiverse communication might work. So we have Wigner on the outside, and then the friend who is going to be manipulated in this simulation on a quantum computer, for example. And I'm going to imagine the friend using this Kit Kat. So when you have we start off with the friend just in a blank state. The friends just at the start of the experiment, and then they are told to measure a qubit that's in superposition. And so if we imagine we start off with both versions of the friend identical, and then the friend measures the superposition. One version of the friend sees 0, another version of the friend sees 1. And so the friend splits into these two parts of the superposition. So we can imagine that friend 0, the one that measured 0, goes into a room labeled 0, and then friend 1 goes into a room labeled 1. Now, friend 1 has been told to write a message for their other self. So they can write on their piece of paper, maybe hello, or maybe something more exciting, to send a message to their other self. And now, what does Wigner do on the outside? So Wigner can't directly transfer the message from one branch to another, because Wigner would have to know what the message is to be able to do that. But there are some tricks to be able to move the observers and their environments between the branches instead. So what Wigner does is swap around friend 0 and friend 0's room to the branch that had friend 1, and then swap around friend 1's branch over to the 0, and then friend 0 ends up with the message from friend 1. And so we've been able to get the friend that measured 0 to receive a message from the friend that measured 1. And there's various kind of subtleties to this, but it's I think it works as a kind of overall idea that you can switch the branches. Now, how does this help us test the multiverse? Well, if you've ever looked a bit into time travel, you might have come across some time travel paradoxes. One of the most famous ones is the grandfather paradox. So that's the idea that if you go way back in time, kill your grandfather before you're born, then you're never going to be born, and we end up with this paradox. That's a kind of classic one. But there's another type called knowledge creation paradoxes. And this is the idea that you can imagine, say, going to the future. Maybe there's a mathematical proof that you've written in the future, and you copy it, you move it back to the past or to the present, and then that becomes the proof that you copied from the future. And in this kind of scenario, there's no logical contradiction happening. Everything's self-consistent, but the question is, where did the information come from? Where did the knowledge that you put in that proof actually come from if nobody thought of it because you copied it from yourself? And I think we can make a similar paradox with this thought experiment, because if you're friend 1 and you received, or you're friend 0 and you received this message from friend 1, then unless friend 1 was actually physically real, you don't have an explanation for how that knowledge came into the world. So it could be a really novel proof, it could be a bug, it could be anything that friend 1 came up with, but you need an explanation for where that knowledge came from. So my suggestion is that this is actually another way of testing against single world and many world theories by how they explain where this information came from in a multiverse communication setup. Now, you might wonder if we can actually message your other self in the multiverse. Unfortunately, that's going to be pretty difficult because we need to be in this setting where you have control over the person that's going to communicate with their other self. So it's not likely going to happen for us talking to our other selves unless we get uploaded onto a quantum computer one day. But we can imagine kind of AIs running on quantum computers and then doing this experiment with them. So just to wrap up, those were the 5 different ways to test the multiverse. We started with reversing a measurement on Schrödinger's cat. Then we had the quantum bomb tester, where some people think the multiverse is needed to explain what happens there. Then we have quantum teleportation, where you can save locality in quantum mechanics if you have this view of classical bits actually being qubits that contain this inaccessible information that they carry. Then we have quantum computing. You could say that large quantum computers that run way faster than classical ones, even if they had all the atoms in the universe, must be accessing the multiverse. And finally, we have multiverse communication, where you can have a knowledge paradox of where did the information come from if you receive a message from elsewhere in the multiverse. So thanks for listening. I don't have a book to show you, but I'm writing one, so you can look out for that in the future. You can also check out the YouTube channel and podcast. I've got some videos that relate to the many worlds things we talked about today, as well as some other aspects of quantum, and a paradoxes series, which is a bit more technical, but gives an idea of these different paradoxes and how to run them with quantum computers and use quantum computing to explain them. So thanks for listening, and happy to take questions.